Ideal gases exposed. Are they even real? Is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. The ideal gas law can be derived from assuming a gas is a collection of point masses that undergo perfectly elastic collisions. We are not going to do the derivation here, but we are going to comment that this model gives rise to the two parts of the definition of an ideal gas. The first is the familiar equation PV equals nRT. The second is at the end DOFPro, yes, I pronounced it correctly, your other professors are doing it wrong, or the internal energy is only a function of temperature. We'll revisit the temperature dependence when we get to the first law of thermodynamics. In terms of molar volume, the ideal gas equation of state is PV hat equals RT. The current exact definition of the molar gas constant is, as you see it here. Just using the first 10 digits is plenty. When can you use the ideal gas law? If you check the molar volume, or RT over P, and find it greater than 5 liters per mole for diatomic gases, such as oxygen or nitrogen, or greater than 20 liters per mole for most other gases, then the ideal gas law is in error by no more than 1%. Do we really need 10 digits in R? What do you do if you are outside the validity range of the ideal gas law? Well, we have a series of videos on real gases and mixtures of real gases, so you'll just have to keep watching to find out. If you start hanging around with mechanical engineers or looking in mechanical engineering handbooks, you will discover that they don't like moles, probably from watching too many spy dramas. Their ideal gas law is PV equals mRT, where m is the mass of the gas in your system. The result is that they have a different value of R for each gas or mixture of gases. I try not to think about it. It's just too traumatic for me. You should be prepared to be polite and respectful if you meet a mechanical engineer and not let your jaw drop in shock. If you check Wikipedia, you'll find that it lists 21 different combinations of temperature and pressure that are used as standard temperature and pressure. The bar charts display the different values of temperature and pressure that are used and their relative frequency. For standard pressure, 101.325 kilopascals, or 1 standard atmosphere, was the most frequent, with 1 bar being the second most frequent. For standard temperatures, the most frequent was 15 degrees Celsius, with 20 degrees Celsius in second place, and the one that I learned in high school, and the one that we are going to use, 0 degrees Celsius, is tied with 16 degrees Celsius for third place. So when someone says, at STP, be sure to ask, at which STP? If you can agree upon an STP, then the molar volume calculated at the standard temperature and pressure is the standard molar volume, V hat sub s. For the possibly common case of 0 degrees Celsius and 1 atmosphere, the standard volume is 22.4 cubic meters per kilomole, 22.4 liters per mole, or 359 cubic feet per pound mole. The molar flow rate of a gas, rather than being specified as moles per time, kilomoles per time, or pound moles per time, is often specified as standard cubic meters per time, or standard cubic feet per time. For the possibly common case of 0 degrees Celsius and 1 atmosphere, 1 standard cubic meter is 44.6 moles, or 0.0446 kilomoles. 1 standard cubic foot is 2.79 times 10 to the minus 3 pound moles. To determine the true volumetric flow rate, you need to know the system pressure and temperature. You can then use the ideal gas law, or absolute temperature and pressure ratios, to calculate the true volumetric flow rate. Let's do an example. For a flow rate of 3.95 times 10 to the 5th standard cubic feet per hour at 285 degrees Fahrenheit and 1.300 atmospheres, calculate the molar flow rate in kilomoles per minute and pound moles per hour. Calculate the true volumetric flow rate in cubic meters per second. Since it's in standard cubic feet, it's easiest to get the pound molar flow rate first. Divide the standard cubic feet per hour rate by the standard cubic feet in a pound mole to get 1,100 pound moles per hour. The conversion from pound moles to kilomoles is the same as from pounds mass to kilograms, and you should be able to convert from hours to minutes, getting 8.32 kilomoles per minute. To get the true volumetric flow rate, multiply the molar flow rate by RT over P. You also have to convert from kilomoles to moles and from minutes to seconds. The result is 3.62 cubic meters per second, which is a pretty big number. You can also just take the temperature and pressure ratios if you think that's quicker. You get the same result either way. Don't forget the temperature ratios have to be in absolute units, in this case degrees Rankine. For ideal gas mixtures, the partial pressure of a species is the same as the mole fraction times the total pressure. Also, the pure component volume, which is much less common than partial pressure, is the same as the mole fraction times the total volume. There is something called a partial molar volume that is related to the pure component volume, but we'll not confuse ourselves with it right now. The sum of the partial pressures equals the total pressure, and the sum of the pure component volumes equals the total volume. These summations are known as Dalton's law and Amigat's law, respectively. Finally, here are some handy relationships which should be obvious, but are really easy to forget under time pressure, such as on an exam or when the problem set deadline is rapidly approaching. The molar concentration of species A in an ideal gas, Ca, is equal to Na over V, or Pa over Rt. The molar density of an ideal gas, which has the same units as concentration, ρ, is N over V, or P over Rt. And lastly, the mass density of an ideal gas, ρ, is the number of moles times the molecular weight divided by the volume, or Pm over Rt. It also works with an average molecular weight. Should that be mass average or mole average molecular weight? The takeaways from this video are 1. There are 2 parts to the ideal gas law. The equation of state, PV equals nRT, and the internal energy is only a function of temperature. 2. The ideal gas law is an error by no more than 1% if the ideal molar volume is greater than 5 liters per mole for diatomic gases, or greater than 20 liters per mole for other gases. 3. We are using an STP of 0 degrees Celsius and 101.325 kilopascals. 4. Molar flow rates are often given in SCM or SCF per time. 5. The partial pressure of a species in an ideal gas is the mole fraction times the total pressure. And 6. The pure component volume of a species in an ideal gas is the mole fraction times the total volume. Thanks for watching. This video was brought to you by the DOFPro team.